Today we are going to discuss triangle congruence theorems. Before we can talk about the triangle congruence theorems, we must make sure that we understand the word congruent. Congruent sides are sides that are equal in measure. When we're looking at congruent sides, we usually use this little tick mark symbol to show that they are congruent. If there was another side, we would use 2. If there was another, we would use 3, and so on. Congruent angles are angles that are equal in measure. When we look at angle measures, we use this arc symbol inside the angle to show congruency. And again, if there was more than one, we could put 2, 3, and so on. Geometric figures are congruent if they have exactly the same size and exactly the same shape. If we look in this example to the right of the arrow, these shapes in green are congruent. They are the same size and the same shape. However, if we look at the red example, these shapes are not congruent. They are neither the same size nor the same shape. So here's a question. If you reflect, rotate, or translate a shape, does it change the shape so it is no longer congruent to the original? Let's think about these 3 transformations. A reflection changes a figure by flipping it. A rotation changes a figure by turning it. And a translation changes a figure by sliding it. None of those movements would cause a change in size or shape, only a change in position. So we can do reflections, rotations, and translations, and they will remain congruent. Congruent figures have corresponding angles and corresponding sides that are congruent. When using geometry notation, we read this statement as follows. Triangle ABC is congruent to triangle DEF. The symbol that I circled, the little wavy line over the equal sign, means congruent. First, let's look at our angles. Angle A is congruent to angle D. This little symbol here means angle. So we can see that angle A here is congruent to angle D here. It's been marked with the arc symbol. Angle B is congruent to angle E. It's got the double arcs. And then angle C, triple arcs, is congruent to angle F, triple arcs. We could also see this if it gave us the measurement. Now let's look at sides. This symbol above the letters can mean side or line. So this reads side AB here is congruent to side DE. We've got the 1 tick mark. Side BC here is congruent to side EF with the double tick marks, and side AC is congruent to side DF. When using geometry notation, order matters. Corresponding parts must match. When we say corresponding parts must match, we have to think about what we learned in previous years about corresponding angles or corresponding sides. I like to imagine that I could cut out this second blue triangle and sit it directly on top of the green triangle. If I did that, then angle A would match up with angle D, angle B would match up with angle E, and angle C would match up with angle F. Therefore, triangle ABC is congruent to triangle DEF. We could also write it as triangle BCA is congruent to EFD, or CAB is congruent to FDE, as long as your corresponding angles are matching up to one another. However, we cannot write that triangle ABC is congruent to triangle EFD. To understand why, let's look at the angles. Angle A and angle E come first in this example. A, E. Are these two angles congruent? No. How do we know? One arc, two arcs. They are not congruent, therefore we cannot write it that way. Let's write a congruency statement and name all corresponding angles and sides. Our statement has been given to us. Triangle QRP is congruent to triangle ACB. Sometimes it helps me when I'm given the congruency statement if I write them like this. So this is showing me that Q is congruent to A, R is congruent to C, and P is congruent to B. So there's all of my angles. So I would say angle Q congruent to angle A, angle R congruent to angle C, angle P congruent to angle B. Now let's look at our sides. For our sides, we have to go from point to point. So this first side right here is made up of QR. That side QR is congruent to, and it matches up to this side here, AC. Next, I have this side, RP, being congruent to CB. And then last but not least, I have PQ congruent to BA. Here are a few practice questions for you to try. Pause your screen at this time and try these examples. Now take a look at the answers. In the first example, you should have gotten that triangle GTR is congruent or equal to triangle VQZ. In the second example, we could have written a congruency statement, and there's more than one way to write this as long as you are matching up corresponding parts of the triangles. But triangle DEG is congruent to triangle FGE. You should have had angles D and F as congruent, angles E and G as congruent, and angles G and E as congruent. For your sides, DG is congruent to EF, FG is congruent to DE, and EG is congruent to EG. Again, you may pause the screen to do the example shown. Now check your answers. In number 1, you should have had triangle BWP is congruent to triangle KMC. I showed you here on the side that the angles BWP make up a triangle. Oops. And the angles KMC make up a triangle. Therefore, triangle BWP and triangle KMC. In order to answer 2, I sketched the triangles. Obviously, mine are not correctly congruent by my sketch, but you get the idea. OV is congruent to SR, VT is congruent to RX, and OT is congruent to SX. Therefore, OVT congruent to SRX. Now we're going to talk about the triangle congruency theorems. Our first theorem is side, side, side. This theorem tells us that if a triangle has 3 sides that are congruent, the triangles are congruent. So we're going to look at this example on the left. Suppose that AB here is congruent to AC here, and BD here is congruent to CD here. And then it says shared side reflexive property. So AD is being shared by both triangles. Therefore, we do have 3 congruent sides and 2 congruent triangles. So we could say that triangle ABD is congruent to triangle ACD. Next, we have side angle side theorem. This theorem tells us that we will have a side followed by an angle followed by a side that is congruent. So again, we're just going to look at the example on the left. Suppose side AD here is perpendicular to side BC. Okay? Remember, perpendicular looks like this. When you have perpendicular lines, they create 90-degree angles. So we're going to have 90-degree angles here. And then we have BD here is congruent to CD here. And then, of course, AD here is that reflexive property because it's shared. So it is also congruent. So we have a side, an angle, and a side, giving us SAS, the side angle side theorem. Next, we have angle angle side. Okay, 2 angles followed by a side. Note, it says the side is not between the 2 angles. It must go angle angle side. All right, so let's look at example number 1. It says shared side reflexive property. Okay, so we've talked about that. So side RS here is shared. Therefore, by the reflexive property, that side is congruent. Okay, then we look here. Remember that these arc symbols tell us that these are congruent. So we have a set of congruent angles here, and we have a set of congruent angles here. Okay, so we can say angle, angle, side. Same on the other side, angle, angle, side. Therefore, it is the 2 triangles are congruent through the angle angle side theorem. Last, we have the angle side angle theorem. The side is between the 2 angles in this theorem. So again, we're just going to look at one example because that's really all that we have time for today. So in example 1, again, we're looking for angle side angle. So we have here angle A is congruent to angle D. So there's our angle. Okay. Next, we have a side, AB here is congruent to ED here. And instead of using the tick mark this time, they just did it red. So there's our side. And then angle B here is congruent to angle E here. Angle, side, angle. You'll notice in example 2, sometimes they're going to actually give you those measurements instead of just the geometric notation. This has been a video on the 4 congruency theorems of triangles. If you need more information, please see the additional resources listed on the website or Google triangle congruency theorems.